Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is DC power. Our objective is to take a close look at the different permutations of power calculations for DC electricity, sometimes collectively known as Watt's laws. Additionally, we'll review power and energy and efficiency calculations and introduce a device used to measure power known as the wattmeter. Power is a pivotal concept for this lecture series and serves to unify a number of previously independent topics. As such, expect numerous shoutouts to previously covered material. If at any time you are presented with material you have never seen or only dimly recall, please take the time to visit these lectures and come up to speed. Recall during the Energy and Power lecture, available at the Big Bad Tech channel, our first shoutout, I introduced the general concept of power, where power is the time rate use or production of energy, where 1 watt is equivalent to 1 joule per second. Energy can take many forms, but is most easily conceptualized as expressing a force for a certain distance, where energy is force times distance. If I move an object that resists me with 5 newtons of force, a distance of 4 meters, I have put 5 newtons times 4 meters, or 20 joules of energy into this system, where 1 joule is the SI unit of energy, equivalent to 1 newton of force expressed at a distance of 1 meter. Energy is the capacity to do work, and I like to think of energy as a quantity of fuel. By way of an analogy, one can think of every single joule of energy as a piece of firewood. In this case, 20 pieces of firewood got loaded into this system. How rapidly one gets this energy into or out of a system is power. Power is the time rate expenditure or production of energy. Power is energy per unit time. In keeping with this firewood analogy, think of the chores you did as a kid. Those of you that live in the colder regions are no doubt intimately familiar with the never-ending chore of cutting, splitting, stacking, and hauling firewood. While essential for survival, this task is not always approached with vigor and potency. Quite often, there is an associated amount of bitching and feet dragging accompanying this task. If on a cold, dark winter night you've ever had a coat thrown in your face and been told to bring in 20 pieces of firewood or freeze to death, you got one of two options. One, you can mope and whine and just pick at it over a long span of time, carrying maybe 2 or 3 logs every trip back from the woodshed. Or 2, just go load a sled with 20 pieces of firewood and drag it back to the house as quickly as possible. The point being, energy is a quantity, whereas power is the rate of change of that quantity. Power is the rate of change of energy over time. In this analogy, energy is like a quantity of firewood, which is a quantity of fuel, and power is how fast that pile of firewood or fuel is built. Again, power is a time rate production or consumption of energy. Let's say we've got two 20 joule tasks, where one is accomplished powerfully over a span of 1 second, and a similar 20 joule task is accomplished less powerfully over the span of 10 seconds. Power is energy over time. The first task power input is 20 joules over 1 second, or 20 joules per second, or 20 watts, where again 1 watt is equal to 1 joule per second. The second task power input in contrast is 20 joules over 10 seconds, or 2 joules per second, or 2 watts. Although both tasks ultimately necessitated the same expenditure of 20 joules of energy, the first task was accomplished in less time with a more powerful 20 watt input, whereas the second task was accomplished in more time with a less powerful 2 watt input. It makes sense. Moving on, let's now tie power and energy with our understanding of voltage and current. Recall during the Basic Electrical Quantities lecture, available at the Big Bad Tech channel, I introduced electrical power, where electrical power is the product of voltage and current. Power equals voltage times current, or in terms of units, 1 volt times 1 amp equals 1 watt. Expressed in shorthand, P equals V times I. Additionally, recall that both the volt and the ampere are derived units, where 1 volt is 1 joule of energy per coulomb of electrons, and 1 amp is 1 coulomb of electrons moving by a point in 1 second. A coulomb, by the way, is a group of electrons, kind of like a dozen eggs, only it is a lot more than a dozen. Using the units to aid us, we realize that our power equation of voltage times current is 1 volt times 1 amp, which simplifies to 1 joule per coulomb times 1 coulomb per second. Coulombs cancel out to yield joules per second, or watts. Think of the properties voltage and current independently, and how each of these two properties influence power. Voltage is a measure of how much energy a group of charges possess. 1 volt is 1 joule of energy per coulomb of charges. Returning to our firewood analogy, this is like how many pieces of firewood you fit in your arms on the way back from the woodshed. If you carry a lot of firewood in one trip, that's a lot of energy or a lot of voltage. If, however, you carry just a handful of sticks, that's not a lot of energy, equivalent to low voltage. Current, in contrast, is a flow rate measurement of how many charges pass by in a given time. 1 amp is 1 coulomb of charges per second. Returning to our firewood analogy, this is like the rate of speed you travel from house to woodshed and back. If you run back and forth real quick, that's a lot of flow or a lot of current. If, however, you just dawdle along and drag your feet, that's not a lot of flow, equivalent to low current. Now think about these properties together. What does the product of voltage and current mean? Consider an occasion characterized by low voltage and low current. Each packet of charges carries only a small amount of energy, and a packet of charges arrives only occasionally. Energy does accumulate, however the rate of change of energy or power is low. This would be equivalent to slowly walking back and forth between the house and the woodshed carrying a stick or two at a time. It's going to take a long time to get the job done because it's not being done powerfully. Conversely, consider an occasion characterized by high voltage and high current. Each packet of charges carries a large amount of energy, and packet after packet of charges arrives in rapid-fire succession. Energy accumulates, and it does so at a tremendously fast rate. This is an occasion of high power. This would be equivalent to sprinting back and forth between the house and the woodshed dragging an ox cart of logs at a time. The job is going to get done real quick because it's being done powerfully. Now that we've got a general understanding of the concept of power, let's discuss the mechanics behind calculating electrical power. Again, electrical power is voltage times current. P equals VI. Consider a 12-volt source and a light bulb modeled as a 60 ohm resistor. An application of Ohm's law demonstrates the light bulb will draw 200 milliamperes of current. We can analyze this system's power from two different perspectives, the source and the load, with the understanding that power input always equals power output. Active elements like voltage sources supply power, whereas passive elements like resistors dissipate or consume power. Power in always equals power out. This does not mean all power gets directed towards useful output, but rather that all power supplied is eventually directed somewhere, useful or otherwise. The source induces a 12-volt rise and supplies 200 milliamperes of current, whereas the load experiences a 12-volt drop and 200 milliamperes of current. Power is voltage times current. 12 volts times 200 milliamperes demonstrates the source is providing 2.4 watts of power, and the load likewise consumes 2.4 watts of power. Power in does indeed equal power out. For such simple circuits, this comparison of input and output power may seem unnecessary. However, for later, more complicated circuits, this makes a great way of checking your work. If at any time the summation of input power does not equal the summation of output power, you've made a mistake and need to re-inspect your numbers. Note that in order to arrive at these power figures, it first necessitated us performing an Ohm's law calculation to determine current. While this is always an option, it is not the most efficient means of performing power calculations, and more expedient methods exist. As you're no doubt aware, the various permutations of Ohm's law demonstrates that current equals voltage divided by resistance, voltage equals current times resistance, resistance equals voltage divided by current. Additionally, you are aware that power equals voltage times current. We can use these permutations of Ohm's law to derive other methods of calculating power. For example, given power is equal to voltage times current, and current is equal to voltage divided by resistance, we can substitute V over R for I in the power equation. This demonstrates that power is equal to voltage times voltage divided by resistance, or voltage squared over resistance. In the above example, 12 volts squared divided by 60 ohms similarly demonstrates that the load consumes 2.4 watts of power. Additionally, given power is equal to voltage times current, and voltage is equal to current times resistance, we can substitute IR for V in the power equation. This demonstrates that power is equal to current times resistance times current, or current squared times resistance. In the above example, 200 milliamperes squared times 60 ohms similarly demonstrates that the load consumes 2.4 watts of power. Let's add these permutations to the power equation to our growing arsenal of tools. Ohm's law demonstrates that voltage equals current times resistance. Current equals voltage divided by resistance, and resistance equals voltage divided by current. The power equation unified with Ohm's law demonstrates that power is equal to voltage times current, power is also equal to voltage squared divided by resistance, and finally power is also equal to current squared times resistance. You note beyond the means of simplifying power calculations, the two additional derivations of the power equation also simplify the practical measurement of power. Using the first equation, where power equals voltage times current, necessitates a technician measure both voltage and current, implying two time-consuming measurements need to be made. First, a technician would have to measure the voltage drop across the load using a voltmeter. Then they'd have to power off the system, break the circuit, insert an ammeter, turn the system back on, get a current reading, and then multiply these readings together to get a power figure. Given these additional permutations, far more efficient means exists. For example, using the second permutation, where power equals voltage squared divided by resistance, simply necessitates a technician measure voltage across a known resistance. Similarly, using the third permutation, where power equals current squared times resistance, simply necessitates a technician measure current through a known resistance. These permutations imply that shortcuts exist that can save you serious time in lab. Additionally, given there exist numerous methods to calculate power, there are ample opportunities to check your work. All methods should yield the same answers. If they don't, you are doing it wrong. Try this set of example problems on for size to see if you're tracking. Given these known values, see if you can solve for power experienced by the system using the most efficient and direct manner possible. Express all answers in proper engineering format to the tens place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features a 270 ohm resistor experiencing a 48 volt drop across it. We're being asked to solve for power. Power is voltage squared over resistance. 48 volts squared over 270 ohms yields 8.5 watts of power. We can use Ohm's law and a different permutation of the power equation as a means of checking our work. Ohm's law demonstrates that current is voltage over resistance. 48 volts over 270 ohms yields 177.8 milliamperes of current. Power is equal to voltage times current. Substituting in our given values similarly demonstrates this resistor is experiencing 8.5 watts of power. Our next problem features a resistor with a color code of green, blue, brown, experiencing 26 milliamperes of current through it. We're being asked to solve for power. A color code of green, blue, brown means 5, 6 with 1 0 after it, or 560 ohms. Power is equal to current squared times resistance. 26 milliamperes squared times 560 ohms yields 378.6 milliwatts of power. We can use Ohm's law and a different permutation of the power equation as a means of checking our work. Ohm's law demonstrates that voltage is equal to current times resistance. 26 milliamperes times 560 ohms yields 14.6 volts. Power is equal to voltage times current. Substituting in our given values similarly demonstrates this resistor is dissipating 378.6 milliwatts of power. Finally, our last problem features an unknown resistor experiencing a 9.9 volt drop across it and 45 milliamperes of current through it. We're being asked to solve for power. Power is equal to voltage times current. Substituting in our given values demonstrates this resistor is dissipating 445.5 milliwatts of power. We can use Ohm's law and a different permutation of the power equation as a means of checking our work. Ohm's law demonstrates the resistance is voltage over current. 9.9 volts over 45 milliamperes yields 220 ohms of resistance. Let's use both permutations of the power equation to double and triple check our work. Power is equal to voltage squared divided by resistance. Substituting our given values similarly demonstrates that the load is dissipating 445.5 milliwatts of power. Power is equal to current squared times resistance. Substituting in our given values similarly demonstrates that the load is dissipating 445.5 milliwatts of power. Given these calculations yield the same result, I've got a reasonable degree of confidence our results are correct. As we did in the Ohm's law lecture, let's plot current and power as a function of voltage for fixed resistance. Consider a 240 ohm resistor that experiences 0 to 24 volts in 2 volt increments. With a 0 volt differential across it, no current flows through it and it dissipates no power. If we step voltage up to 2 volts, an application of Ohm's law demonstrates that we should expect 8.3 milliamperes of current and the resistor to dissipate 16.7 milliwatts of power. If we step voltage up to 4 volts, an application of Ohm's law demonstrates we should expect 16.7 milliamperes of current and the resistor to dissipate 66.7 milliwatts of power. If we perform the same calculations in 2 volt increments, we should observe every increase in voltage to result in proportional increase in current. Notice how the current at 4 volts is twice that observed at 2 volts. If we step voltage up to 8 volts, the current at 8 volts is twice that observed at 4 volts. If we step voltage up again to 24 volts, the current at 24 volts is 3 times that observed at 8 volts. In short, Ohm's law is a linear property. and when current as a function of voltage is plotted, the results speak for itself. Every increase in voltage results in a proportionate increase in current. Power, in contrast, is not a linear property, but rather geometric in nature. Power at 4 volts is 4 times that observed at 2 volts. We step voltage up to 8 volts. Power at 8 volts is 16 times that observed at 2 volts. If we step voltage up to 24 volts, power at 24 volts is a full 144 times that observed at 2 volts. In short, power takes off like a rocket ship because it is a nonlinear geometric property. It is for this reason accurate voltage and current measurements are so important. Any increase in voltage results in a proportionate increase in current and a geometric increase in power. Lacking accurate measurements, it would be all too easy to reduce an otherwise functional component into a useless smoking husk. Moving on, I present you with your existing arsenal of tools: 3 versions of Ohm's law and 3 permutations of the power equation, 6 arrows with 6 sharp tips. Can you use these 6 arrows to make 6 more sufficiently deadly arrows for your quiver? If you are as mathematically competent as I expect you to be, you should be capable of algebraically manipulating these equations to solve for unknown quantities. For example, given known voltage and known power, we should be able to algebraically manipulate this entry to solve for resistance. Start by performing the inverse operation of both sides to get resistance on top. Multiply both sides by voltage squared. Voltage squared cancels out on one side, where we're left with resistance equals voltage squared over power. This is yet another arrow in our quiver. This equation implies that given known voltage and known power, we can solve for unknown resistance. Similarly, given known power and known resistance, we should be able to algebraically manipulate this same entry to solve for voltage. Multiply both sides by resistance. Resistance cancels out on one side, and we're left with power times resistance equals voltage squared. Square root both sides. Square root cancels out on one side, and we're left with square root of power times resistance equals voltage. This is yet another arrow in our quiver. This equation implies that given known power and known resistance, we can solve for an unknown voltage. You'll note this arrow is particularly sharp because it necessitates the user first multiply power and resistance and then take the square root of the product. By placing power times resistance in parentheses, it makes it painfully obvious that the product needs to happen before the square root operation. Do not poke yourself in the eye with this arrow by neglecting the order of operations. You now have 8 arrows in your quiver. As an exercise to the viewer, I invite you to solve for the following additional algebraic permutations. Given the original power formula, where power equals voltage times current, solve for the following. Given known power and known current, solve for voltage. Given known power and known voltage, solve for current. Additionally, use the permutation power equals current squared times resistance to solve for the following. Given known power and known resistance, solve for current. And finally, given known power and known current, solve for resistance. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given power equals voltage times current, and given known power and known current, we should be able to algebraically manipulate this entry to solve for voltage. Divide both sides by current. Current cancels out on one side, and we're left with voltage equals power divided by current. This equation implies that given known power and known current, we can solve for an unknown voltage. Similarly, given power equals voltage times current, and given known power and known voltage, we should be able to algebraically manipulate this entry to solve for current. Divide both sides by voltage. Voltage cancels out on one side, and we're left with current equals power divided by voltage. This equation implies that given known power and known voltage, we can solve for an unknown current. Add these 2 arrows to your quiver for a current total of 10. Given power equals current squared times resistance, and given known power and known resistance, we should be able to algebraically manipulate this entry to solve for current. Divide both sides by resistance. Resistance cancels out on one side, we're left with power over resistance equals current squared. Square root both sides. Square root cancels out on one side, and we're left with the square root of power over resistance equals current. This equation implies that given known power and known resistance, we can solve for an unknown current. As previously, you'll note this arrow is particularly sharp because it necessitates the user first divide power by resistance and then take the square root of the quotient. By placing power over resistance in parentheses and extending the square root all the way to the bottom of power over resistance, and makes it painfully obvious the division operation needs to happen before the square root operation. Again, don't poke yourself in the eye with this arrow by neglecting the order of operations. Finally, given power equals current squared times resistance, and given known power and known current, we should be able to algebraically manipulate this entry to solve for resistance. Divide both sides by current squared. Current squared cancels out on one side, and we're left with power over current squared equals resistance. This equation implies that given known power and known current, we can solve for an unknown resistance. Ohm's law, when unified with a power equation, is incredibly versatile and can be used to double-check your work. In this spirit, I present to you what I like to think of as the grand unified theory of voltage, current, resistance, and power, sometimes collectively known as Watt's laws. This visual aid is a highly recommended addition to your cheat sheet. You'll note, given the numerous methods available, there exist multiple routes to a single solution. If one path is blocked, try another. I am encouraging you to find the method that works best for you. Develop your own style of problem solving and troubleshooting. Get good at it, get efficient, and don't make mistakes. If I present to you a method you totally suck at, practice it more or just plain don't use it. Use a method you're good at. Use methods you like using. My only demand is that you get correct results in the quickest manner possible. Let's put your understanding of these permutations to the test. I've given you 6 new arrows, and here's 6 new targets. Go fetch. Given the known values for each scenario, see if you can solve for the third unknown value using the most efficient and direct means possible. While you're there, see if you can use another algebraic permutation to check your work. Ideally, both calculations should yield the same result. Express all answers in proper engineering format to the 10th place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Our first problem features an element consuming 600 watts of power and experiencing a 120 volt differential across it, where we're being asked to solve for the current through it. Current is equal to power divided by voltage. 600 watts divided by 120 volts yields 5 amps of current. A supporting calculation verifies this result. 120 volts times 5 amps does indeed yield 600 watts of power. Our next problem features a resistor with a color code of blue, gray, brown, gold, known to be dissipating 1.2 watts of power. We're being asked to solve for the voltage across it. A color code of blue, gray, brown means 68 with 1 0 after it, or 680 ohms. Voltage is equal to the square root of power times resistance. The square root of 1.2 times 680 demonstrates this resistor should be experiencing a 28.6 volt drop. The supporting calculation verifies this result. 28 volts squared divided by 680 ohms does indeed yield 1.2 watts of power. Our next problem features an unknown resistor known to be dissipating 6.4 watts of power and experiencing 80 milliamperes of current through it. We're being asked to solve for the unknown resistance. Resistance equals power divided by current squared. 6.4 watts divided by 80 milliamperes squared demonstrates that this is a 1 kilo ohm resistor. The supporting calculation verifies this result. 80 milliamperes squared times 1 kilo ohm does indeed yield 6.4 watts of power. Our next problem features an unknown resistor known to be dissipating 1.8 kilowatts of power and experiencing a 240 volt drop across it. We're being asked to solve for the unknown resistance. Resistance is equal to voltage squared divided by power. 240 volts squared divided by 1.8 kilowatts demonstrates that this is a 32 ohm resistor. The supporting calculation verifies this result. 240 volts squared divided by 32 ohms does indeed yield 1.8 kilowatts of power. Our next problem features a 50 ohm resistor known to be dissipating 700 watts of power, and we're being asked to solve for the current through it. Current is equal to the square root of power divided by resistance. The square root of 700 watts divided by 50 ohms demonstrates the resistor should be experiencing 3.7 amps of current. The supporting calculation verifies this result. Power is equal to current squared times resistance. 3.7 amps squared times 50 ohms does indeed yield 700 watts of power. Finally, our last problem features an unknown resistor known to be dissipating 270 milliwatts of power, experiencing 15 milliamperes of current through it. We're being asked to solve for the voltage drop across it. Voltage equals power over current. 270 milliwatts, or 15 milliamperes, demonstrates this resistor should be experiencing an 18 volt drop. A supporting calculation verifies this result. 18 volts times 15 milliamperes does indeed yield 270 milliwatts of power. Alright, hopefully that last set of example problems went well for you. If not, by all means rewind that last section and correct any mistakes you may have made. Again, it's often not the electrical concepts students struggle with, but rather the algebra and numerical literacy that hinders forward progress. As a general study skill advice, figure out what your problem is before you go see a tutor. No sense in practicing something you already know. Get to the root of the problem quickly and move on. Is it math? Is it numbers? Is it electrical concepts? Seek help on that topic and that topic alone before you move on.